Good evening. Hope a few more of you will get on as we go along. It seems like everybody's enjoying the sunshine for a while tonight. Tonight we want to talk about vectors. Maybe a lot of you have seen these before. I'm going to go rather fast, but since it's a video, you can replay it as many times as you want. I'm going to cover sections 11.2 and 11.3 tonight. Really what we're constrained to here is vectors in the plane, in the Euclidean plane. And higher mathematics, there are abstract sorts of vectors that are sets of functions and so forth. We aren't going to deal with that. We'll say a vector in the plane is nothing more than a directed line segment. What does that mean? That means a line segment together with specification that one end is the initial point and the other end is the terminal point. You may have seen these in another class. Sometimes they do them at the end of trigonometry or something like that. They're common in physics if you take a physics class. And we're going to do these in higher dimensions too eventually, but for now we'll just do them in the plane. And so here's a point, let's say 1, 1, and here's the point 3, 2. I label this one point P, and this one point Q. I can say here's the vector from P to Q. It's just this line segment together with, I'll put an arrowhead on it to indicate this is the initial point, this is the terminal point. That's how we draw vectors, is arrows. Then we can say, what do we talk about the length of a vector? Suppose I have a vector from P to Q like that, with the coordinates of P, x0, y0, and Q having coordinates x1, y1. What should we say its length is based on that kind of diagram? Well, we'll just use its Euclidean length of the line segment that it is. And then it's very easy to figure. It's just the Pythagorean theorem. Told you part of this is kind of easy. But what we're getting at is we're trying to move up to vector calculus. We first want to know what it is we're talking about. Right? So if this point has coordinates x0, y0, and this point has coordinates x1, y1, we just make a triangle and say, oh, this length, this one is a displacement x1 minus x0, and this one is a displacement y1 minus y0. And so by the root sum square, the Pythagorean theorem says that the length of this side, which we will call the length of V, if this is the vector V, is then the root sum square of this by the Pythagorean theorem, right? It's x x1 minus x naught squared plus y1 minus y0 squared, square root. There it is. There's first definition regarding some property of vectors. Also, if you look at this, we notice that there's a displacement in the x direction and a displacement in the y direction. We can call those something too, right? Let's call those the components. The components of V And we get tired of writing two letters, P, Q. Let's suppose P is a vector from P to Q with these coordinates. R then, V1 will be the displacement in the x direction, right? Here's the x, y system, then it goes from x0 to x1, and its displacement is x1 minus x0, and the displacement in the y direction is y1 minus y0. So we can say better, writing length that way, the length of the vector, also called the norm, or magnitude of the vector, becomes just the square root of v1 squared plus v2 squared. Furthermore, we're going to say, boy, these are not good tonight. And we will say that two vectors in the plane, regardless of where they're placed, are equivalent if they have the same components. Equivalent or equal. All components identical. So vector V equals vector W if and only if we write IFF sometimes meaning if and only if their first components are equal and their second components are equal. Another property of vectors. Now we can also talk about the direction a vector goes. Let's say the direction or direction angle, because there's also going to be a direction vector coming up. Direction or direction angle of a vector V with components, and we'll write V equals V1, V2. With the idea, it doesn't actually matter where its initial point is, as long as it has these components, it's equal to any other vector with these components. So you can parallel displace it, and it's still an equal vector. You move it around some other point in the plane. So we'll just say V equals this, with the idea that all vectors that have identical components are equal. The direction angle of V is, what shall we call it? Well, here's our vector V, and here's component V1, and here's component V2 is the displacement in each of these directions. It can be negative, right? If it goes left, it's got a negative component V1. If it goes down, it's got a negative component V2, because this is just the difference in the y coordinates, and this is just the difference in the x coordinates of the 2 points. Oops. 0 before better be consistent. There's that vector. The direction angle will be this angle counterclockwise from the positive x direction. If you like, from the vector of components 1 and 0, so any vector pointing in that direction. So there's the picture, and how will we compute that then? Well, from trigonometry, the tangent of theta is opposite over adjacent. And so we could say, oh, that means that the direction angle, let's call it theta, the angle theta counterclockwise, satisfies tangent theta equals b2 over b1. It reminds you of trigonometry, right? Tangent theta equals y over x. That's what it is, y over x. Moreover, you remember in trigonometry, this tangent theta equals y over x applies even when y over x is negative, right? It goes around the unit circle. And so we can actually do this in any quadrant. I do it in the first quadrant just for simplicity to show, right, with a triangle. But it actually holds in any quadrant, right? However, maybe you remember that there are two directions that have the same tangent, right? Remember, if I take a vector in this direction, this angle clear out here has the same tangent as this one. Angles directly opposite have the same tangent. So we'll find the direction angle by saying tangent theta equals b2 over b1 in the correct quadrant. We don't want to pick the one in the opposite quadrant. People like to write this relation because it's easy to write down, but to actually calculate it, it's a little more thinking. All right. If you really think about it, what is theta equal to if you just want to say theta equals in terms of the, well, you might want to say, oh, it's arctangent b2 over b1, right? Well, sometimes, right? It can be arctangent of b2 over b1 if you're in quadrants 1 and 2, because, I'm sorry, 1 and 4, because the arctangent always gives you an angle between plus and minus pi over 2, right? And so I'll put a vector at the origin. That's the easiest way to draw them. Here's a vector v. Goes out in this direction, v2 and v1. And this is really why we like drawing them at the origin. If we put the vector at the origin, right, then its components are the same as its terminal point, right? Because you go over v1 and up v2 from the origin, you get to the point also v1, v2. Notice that when I draw vectors by their components, I draw them with angle brackets to represent a vector of components. But if I'm looking at a point, then I'll draw these round brackets. So when the vector is at the origin, and if and only if it's at the origin, the components of the vector are actually equal to the coordinates of the terminal point. So that's convenient. And then it's very easy to calculate the direction angle too. We just say, oh, hold on. Oh, did it open? Okay. Can I grab a chair, please? Yeah, go ahead. Thank you. Now, it can be the arctangent for quadrants 1 and 4, because in those quadrants, right, that will be the value of the arctangent. Quadrant 1 and quadrant 4. Now, if you're over here though, suppose I have this kind of vector in quadrant 2 or 3, and I took the arctangent, what would I get? Maybe you remember from trigonometry, you won't get this angle. Instead, you'll get the angle of the terminal ray that's in quadrant 1 or 4 with the same tangent. It'll be the one directly opposite. So this one here, this negative angle in this case, will be the arctangent of b2 over b1. So what shall we say is the angle that's here? Oh, it's just this 1 plus pi, right? There's pi radians to a straight angle. So we'll say if the angle is in quadrants 2 or 3, remember how the quadrants go? Quadrant 1 is where both coordinates are positive. Then we rotate counterclockwise to quadrant 2, quadrant 3, and quadrant 4, and we use Roman numerals of the quadrants. Okay? All right, so arctangent V2 over V1 plus pi, if this is in quadrant 2 or quadrant 3. Now, actually, you can also add any multiple of 2 pi to this, and it works just as well too. You just need to have the angle point have its terminal ray correct direction there. And then you have to have separate ones for the quadrantal angles, right? Of straight up and straight down, those two quadrantal angles, because if you take vector with V1 equal to 0, you get a division by 0 here. So if V1 equals 0, but V2 is bigger than 0, then you've got no x component but a y component, and it goes up, so the angle must be pi over 2. Then if V1, the first component, is 0, but V2, the second component, is negative, right? Then the vector has 0 horizontal displacement, but a negative vertical displacement. Your angle is here at 3 pi over 2, or you can say minus pi over 2. Either way, let's call it minus pi over 2. And now you've got something that gives you the direction angle. This is what you'd have to keep track of if you wanted to write a formula for it. So people just write this down and figure what quadrant it's in, and then they can figure out the angle that way. It's easier than memorizing such a complicated rule. Technically, what people like to do in practice is they like to make angle theta either between 0 and 2 pi within one whole rotation positive, or between minus pi and pi. Both conventions are used, particularly the latter one in mathematics, minus pi to pi. And if you do that, then you can't use this plus pi here, because you can get an angle in quadrant 1 and add pi to it, it gets bigger than pi. So if you want to follow the convention and make it between minus pi and pi, then you'd have to do this if it's in quadrant 3. Add pi. So that you come up with a negative arc. Let's see. Figure this down. I guess you'd subtract pi. Yeah, see, you put minus pi if it's in quadrant 3. So you start out in the first quadrant and you subtract pi. But if it comes out in the fourth quadrant, then you want to add pi. So you get, let's do this. It's plus pi in quadrant 2. And then it's arctangent of V2 over V1 minus pi. So that you come out between plus and minus 180 degrees, plus and minus pi. This will be for quadrant 3. And now you've got an even more complicated rule. Fortunately, this is programmed up. If you program in any higher level language like MATLAB or C++, those kinds of things, then there will be a command in there called ATAN2, and this one can be calculated for you. So if you're ever out in industry and you don't want to figure out the quadrant, you can just go ahead and do this. In many languages, programming, Fortran too, if you do that, old language, it's an ancient language, but it's actually got important, carefully checked numerics, so people still use it today. And this function that gives you this is ATAN2, and then you put y first and then x. Gives you the arctangent. Oh, gives you the arctangent with the quadrant, like that. Theta. You can't usually put Greek letters in, maybe write it in English. Theta is your variable, so you can calculate like that on a computer. But we'll put y first and then x. And then it takes into account the quadrantal angles on the y-axis. it takes into account which quadrant you're in and follows all these rules precisely. I say that just in case you want to use that for the test if we happen to have an angle that's not a special angle. In practice, what's going to happen on the problems is I'm going to give you special angles, an angle that's a multiple of 30 degrees or 45 degrees, and have you just use this relation and the quadrant you know it's in to calculate the angle exactly. So this is important for non-special angles. In practice, most of these problems will be special angles. So we're screaming for an example. We got all sorts of theory here. Right? No example. So let's do this. Find the components, length, and direction of the vector from the point with coordinates 1, 1 to the point with coordinates 1 plus square root 3, 2. How about that? Suppose I'm from that point to that point. I like to draw these. Once you picture these in your mind, I think you're a much better mathematician at this. Despite all the formulas, the picture is worth 1,000 words, as they say, right? So I'm going from the point 1, 1 to the point 1 plus square root 3, 2. So square root 3 is about 1.732. So here's 2, 3. It's about here somewhere. Here's square root 3 is about this far. And so goes 1, 1 to 1 plus square root 3. That's the x component. B1. I should compute it over here. B1 is the difference in the x components. It's 1 in the x coordinates. 1 plus square root 3 minus 1 is square root 3. B2 is the difference in the y coordinates. 2 minus 1 equals 1. So you compute the components just by subtracting the coordinates, x coordinates and y coordinates. That's all they are, the displacement. So this displacement, B1 is square root 3. The other displacement, B2 is 1. That is the difference in the coordinates there. 2 minus 1 is 1. And so here's my vector. It goes to this point here. 1 plus square root 3, 2. There's my vector V. Now, we can write V in terms of its components is square root 3, 1. So there's the first part, find its components. And I'll write that notation for it. Any questions so far? Fast and furious, but hopefully it's not too hard. All right, now we want to have the length. The length is very easy. The length of V is just the root sum square of its components. So it's square root of square root 3 squared plus 1 squared. Well, that's square root 4. It's just 2. So this vector is exactly 2 units long from here to here. That was computed by the Pythagorean theorem. Its direction angle satisfies, regardless of what quadrant, tangent theta equals V2, 1 over V1 square root 3. Now, what does that make the direction angle exactly? When you can compute it exactly, I want you to do that. I want you to get a calculator approximation. On some calculators, it will tell you the exact angle, and you're welcome to do that on the test, but I want you to be able to do these by hand also. What you might remember is that doesn't look like points on the unit circle, right? This is, I'll use the unit circle to find theta. This is already 1.7. It's outside the unit circle all by itself. What you do is you recognize that if you divide the top and bottom by 2, 1/2 square root 3 over 2 is a point on the unit circle. Maybe this is y, and this is x for theta, or V2 and V1, I guess I'm better saying for the vector, y and x components. Or what else could happen? The only other ratio 1 to square root 3 on the unit circle is if you take negative this one over negative this one. It could be that your components are -1/2 and minus square root 3/2. One is the case, either V1 is this and V2 is this, or V1 is this and V2 is this. And those are the only 2 points that have that tangent. Well, you look on the unit circle, we're trying to find the angle, so I use the unit circle to find the angle. And if I take this one, 1/2, and square root 3/2, I come into the first quadrant here, but if I take this one, it's the angle directly opposite. It's always directly opposite. -1/2, negative square root 3/2. Which one is it? Well, the original vector has positive components. It's the first quadrant, so we throw this one out. We want quadrant 1 by virtue of the components of your positive. We throw that one out. We say it's this angle right here, theta. What is it? We're how to do these from trigonometry, hopefully, right? You drop the perpendicular to the x-axis, always by convention. You notice that since this is at 1/2, I forgot to write it on here, didn't I? 1/2. The length of this segment here is 1/2, and since this one goes up to square root 3/2, the length of that one is square root 3/2. It's a unit circle out in 1 30, 60, 90 triangle, right? So theta, evidently, is 60 degrees, also known as pi/3 for trigonometry. Make sure you remember your special angles for this. Theta is pi/3. That's my direction angle. Okay. You just use tangent theta equals y/x. Figure whether it's this ratio or minus the top or minus the bottom, by which quadrant it's in, and then you can either use a special triangle to figure the angle exactly if it turns out to be a oval of 30 or 45 degrees. And if not, you can use the tan2 function or your calculator with this list I gave you here. It's in quadrants 1 or 4, just take the arctangent. If it's in 2 or 3, just take the arctangent plus pi is the easy way I remember it. Then I won't demand that you put it between minus pi and pi radians. You can take any angle that goes to the terminal, right? All right. So the vector from here to here has these components, square root 3, 1. So we write v equals this vector of its components. The length of v is the root sum square of its components, and the direction angle satisfies tangent theta equals v2 over v1, and you can figure on the unit circle in this case exactly what angle it is. Now, really, in applications, what we want to do is add vectors and that sort of thing, because velocities and other quantities in nature behave that way. So let's define addition of vectors. Sum of two vectors, v and w, components v1, v2, w1, w2, defined in the easiest way, you just add component by component, v1 plus w1, v2 plus w2. Add component by component. That'll be the definition. Addition of vectors. Sum of two vectors is a vector whose components are added correspondingly. Why would we want to do that? Is because that's the way things like velocity behave in nature, right? If you go to classical mechanics, Newtonian mechanics, they call it. If you take a vector, in fact, let's do it this way. This would be like an Einstein train experiment, except Einstein did the train experiment to say that this messes up when you get near the speed of light. But here's a caboose of a train or something, and it's charging along. And if it has this velocity vector with which it's moving, and then there's somebody standing on the train here who throws a ball up like this at this direction, maybe there's a W. What is the net velocity of the ball with respect to an observer standing on the ground? Well, the observer in red. right? The way it works in classical mechanics, how you can go out and measure it, is you take this vector v and this vector w, and you put them end to end. Here's v, and here's a copy of w. And the vector like this is the velocity with which the ball moves with respect to the observer. I guess I should make it from this person's hand or something. So there's v and there's w, plus w like that. This vector, however, is precisely what we're computing here, right? Because you add the x components, this one, and you get this one, right? You add the y components, nothing from this one and this one, and you get this one. Adding component by component is precisely what does what we see in velocity charts, for instance. Okay, forces behave like this too. They combine by putting vectors in when you're not near the speed of light. Near the speed of light, this gets messed up. So that's the motivation for this. And now we also have another thing. We can have multiplication by a scalar. In this context, when we say scalar, we just mean a number. Multiplication by scalar number, as opposed to a vector, works like this. Number is c. We'll say c times v is the vector with components each scaled by c. cv1, cv2. That'll be multiplication by a number. And then this implies subtraction. Right? If you want to take a vector v minus a vector w, what should you do? Following numbers, you say, oh, that must be v plus minus 1 times w. Right? And if that's the case, well, minus 1 times w is just where you multiply each component by minus 1, so it's minus w1 minus w2. And then you add those component by component, and you get v1 plus minus w1, v2 plus minus w2. So what you infer from that is when you make these definitions, subtraction is also just component by component. First one minus the second. First one minus the second one. Second, subtract the first components to get the new first component, subtract the second components to get the new second. So there's addition, subtraction, and multiplication by a number. You might think, well, maybe we can multiply two vectors, and actually we can, but it's next section, so we'll maybe get to that at the end of it. But what you notice from this definition, then, this definition is there's some very interesting geometry that occurs. You have to think about it for a minute, but what's happening is when you make this definition, here's v, here's w. Sum of two vectors defined component by component is equivalent to taking the one vector and placing its tail at the head of the other one. So you just take a copy of it, a vector equal to w, put it like that. Sometimes we'll label it w. Or it turns out if you add these in opposite order, the same definition, w plus v, this is a proof, is w1, w2 plus v1, v2. And according to the definition here, adding these two vectors gives you w1 plus v1, w2 plus v2. So by definition of addition, w plus v, adding in the opposite order gives you this vector. But now the components are just numbers, right? From arithmetic, we know we can add numbers in either order. v1 plus w1, v2 plus w2 is then equal to this. And all that's just v plus w. So there's a proof of what we call the commutative property of addition. Just like numbers can be added in either order, vectors can be added in either order. And so that means if I have V plus W and I get this one, that makes this kind of result. Then I can also add it in the other order, take W and then take a copy of V and put it at the end of W and get to the same point. We draw this parallelogram as a nice way of thinking of vector addition. You draw V and W vectors at a point. V plus W is the diagonal of the parallelogram formed by parallel transporting V or W to complete this parallelogram. So that's addition as the parallelogram diagram, and sum of two vectors is the diagonal of the parallelogram they determine. How well shall we do with subtraction then? Subtraction has an interesting, slightly different picture. If I take a vector V and I take a vector W, what shall V minus W be? I'm going to say it's this one actually, from the end of this one to the end of this one, V minus W. Technically, when you subtract vectors, it becomes another vector of the same point, so I should really draw it here. But since we say vectors at any point are equal, say this is a vector equal to V minus W is by parallel transport. So people like to draw it this way instead of drawing the actual one. And how do I know that? Well, the idea is if I take W and add it to V plus W, V minus W, excuse me. If I add these two vectors together, what am I supposed to get? Well, subtraction, these cancel out. I'm supposed to get V. Sure enough, that's what this is, right? So this plus this we know adds up to V. So it must go to the endpoint of V here. That's what subtraction is. It's a difference of two vectors is the vector that goes between their endpoints. The vector that's subtracted to the first vector, so that this holds. But if we add vectors, then the sum of the vectors is the diagonal of the parallelogram. Those make immense help in vector diagrams when you remember. But actually computing these is really easy. Right? We need another example. Suppose B is the vector 2, 3, and W is the vector 4 minus 1. What is the vector 2V minus 3W? Suppose I want to compute that one. Easy. Look how easy those definitions are. But you follow the rules of precedence of algebra. You do multiplication, unless parentheses force otherwise, you do multiplication before addition and subtraction. Then you do multiplication left to right, and then addition and subtraction left to right. So you first multiply V by 2, and remember multiplication by a number, a scalar, just multiplies every component by that. So I take 2 times 2 is 4, 2 times 3 is 6, and then I'm going to subtract off 3 times W, I multiply each of these by 3, 12 minus 3. So this is equal to this. And now when I subtract, remember, I just subtract component by component. So I get 4 minus 12 is minus 8. And 6 minus a negative 3 is 6 plus 3, or 9. So there's the vector 2V minus 3W. Now suppose I take vector minus 2, 1, and I add it to the vector 4 times the vector 1, 3. Right? Now what I'm going to do, again, multiplication before addition. So I take minus 2, 1, the first one, and then 4, 12, multiplying each component by 12. And now I add component by component. 4 plus minus 2 is 2. 12 plus 1 is 13. And there's this vector plus 4 times. So arithmetic vectors is very easy. And now it suggests another notation that's used in a lot of the sciences. We introduce the following definition. You see this used in the sciences and it kind of makes sense, but then when you see it derived in here, it makes so much more sense. Suppose I let I with a little arrow over the top, and note the vector 1, 0 that's along the positive x-axis, and normally we place it at the origin. So it goes from the origin to the point 1 unit over. There's I, right, along the x-axis. And then we let j be the vector with x component 0 and y component 1 going up to the point 0, 1. 1 unit up the y-axis. So here's j. With that notation, we can then rewrite all these vectors in an ij notation. Now, any vector v with components v1 and v2 has the following situation. v1, let's write it, v equal v1, v2. We know by addition that this is equal to the vector v1, 0 plus 0, v2, right? Because you add component by component. This plus this is v1, this plus this is v2. Sure enough, that works. Now I can also pull out a number here. I could call this one v1 times the vector 1, 0. That's the way multiplication by a scalar works, right? v1 times 1 is v1, v1 times 0 is 0. And similarly, I can factor out a v2 out of here, v2 times the vector 0, 1. But this is just v1 times the vector I called I, plus v2 times the vector I called j. This is alternate notation that will mean exactly the same thing as this for v. So these are interchangeable, and now you can add and subtract and take scalar multiples of vectors in this notation too. So I can take this kind of a thing. What is 3 times the vector I minus 2j minus 2 times the vector minus 4j? If I write minus 4j, a 0i is implied, right? I mean, it's just a vector with only a y component. Well, again, we multiply through, and instead of multiplying each component this in here, we recognize that the components here are 1 and -2. So we multiply those each by 3, and this 1 becomes a 3. We have 3i minus 6j, multiplying each component by 3. And then we can subtract off this vector. 2 times minus 4j is 8j. Well, just like in arithmetic with numbers, the minuses cancel, right? This takes minus 1 times this vector, and this takes minus 1 times it again. So you can cancel these out, put plus. And now we can say this is 3i plus nothing is 3i. And minus 6j plus 8j is 2j. Just adding components, right? Minus 6 plus 8, you add components just like you in the other notation. The other notation, this would be what is 3 times the vector 1 minus 2 minus 2 times the vector minus 2 times the vector 0 minus 4. So this is the other notation, means the same thing as this. And you just take 3 times this one. Say it's 3 minus 6. Plus, if you like, 0, 8, canceling the minuses. And that's that step. And then you add component by component. You get 3, and minus 6 plus 2 is, plus 8 is 2. You get the same result. So this is just another notation doing the same thing. Those are very easy problems in this section. They're just, the hardest thing is calculating that direction angle, I think. Now what we can do is introduce a product of vectors, right? In addition and subtraction of vectors and multiplication by a number, but there's a vector product known as the dot product, and there's one more coming up too called the cross product, but that'll only be in 3 dimensions. So the dot product of two vectors in a plane has this definition. Let V1, V2 dot W1, W2 have this very easy definition. You might think, why do we make it so easy? Surely that can't be useful, but amazingly, it's extraordinarily useful. It says this times this plus this times this will define the dot product of these vectors to be V1, W1 plus V2, W2. That's all there is to it. It's a very easy definition. This actually, the book has a lot to say about it. It's a very important quantity. So that'll be the definition. And now, I just do a simple example. If I take the vector 2 minus 3 and I dot product it with vector 5, 7, then I just take 2 times 5 plus minus 3 times 7. And it's 10 minus 21 is minus 11. And now you suddenly realize that the dot product of two vectors is actually not a vector, but a number. You might think you multiply two numbers to get a number. I multiply two vectors, I get a vector. No, on the dot product of two vectors is actually a number. That's what this is calculating. Now the proof is non-trivial, so I'm going to leave it out just for trying to make sure we keep caught up this semester. It's hard to keep up. Here's a nice theorem that shows why the dot product is so useful. If you take the dot product of two vectors, V and W, it always comes out to be length of V times the length of W times cosine of theta, where theta is the angle between them. It won't be the angle in standard position to either of them generally. Theta is the angle between them. You might say, well, wait a minute, what is the angle between them? Here's a vector V, and here's a vector W. Maybe I want to take the angle around this way from V to W, or maybe I want to go from W to V. Which is it? I wonder. By the angle between them will always mean the smaller of the two angles that we can form in that way, taking counterclockwise positive. So this is an angle between 0 and pi, 0 and 180 degrees. It's this one right here. Always it will be the angle between 0, 180 degrees, or equivalently 0 and pi radians. With that definition of the angle between them, this theorem always holds for non-zero vectors. If one of them is a zero vector, then there's not a uniquely defined angle between. And speaking of which, when I put not the zero vector, that means the zero vector is the vector with all components 0, right? 0 is this component. And this is a very important vector, actually, because just like in arithmetic, you have something called an additive identity, right? If you add 0 to any number, you get that number back. So we call 0 the additive identity. It retains the identity of the number you added it to, right? Similarly with vectors, if you add a vector to the 0 vector, right? It retains its identity. You just get the original vector back. So 0 is the additive identity. And then you can define additive inverse. The additive inverse of V is minus V because V plus minus V adds up to the 0 vector, for instance. So you can actually develop a whole vector algebra, right? So if you take any vector, you do vector addition of V to minus V, to find out you get the 0 vector. So minus V, the vector with the minus the components of V, is called the additive inverse. And you can go on with those other properties. These vectors can have the usual properties of algebra. The commutative property you can add in either order we proved. There's also an associative property, V plus W plus U equal to V plus W plus U. So you might guess these things, but they have the usual properties of arithmetic. In fact, if you really think about it, what we've done is generalize the notion of arithmetic of numbers. Think about it. What if I had vectors that just had one component? What would I do? I'd say similarly, 3 plus 7 adding component by component is just 10. So number addition is just one-dimensional vectors. All we've done is extend this to 2 dimensions. We've generalized. The only thing is that here, when we take the product of 2 vectors, the dot product, we say, oh, that's 3 times 7 is 21. We just multiply them by component. When we generalize it, there's a trick. It's not a new vector. It's actually, it's first times first component plus second times second component, the number that comes out. So this actually does generalize what you saw in one dimension. You think of this as being the number 21. All right, so here's a classic example that I like. Find the angle between the 2 vectors, P components 1 and 3, and W with components minus 1 and 2. Wonder what the angle is between those. Here's what this theorem does for you. It tells you how to define the angle between vectors. You can actually, in higher mathematics, say, what is an angle between vectors? I mean, when I look at it, it looks like there's something there. But how do I say what it is if I just have these vectors with numbers? What you do is you define the cosine of the angle be the number such that V dot W is length of V, length of W times whatever cosine theta is supposed to be. And that defines the cosine of theta. Then you can take the arc cosine to get the angle and say that defines the angle. So there really is an angle just by making this as a definition of cosine theta. If you want to do it that way. In higher mathematics, sometimes they think abstractly. It's a way one can actually introduce rigorously the definition of angles. All right, so what is the angle between these? Now, in trigonometry, assuming angles, you can derive that property as a theorem, is what we said. Find the angle between these 2 vectors. Here's what we do. By our theorem, we calculate V dot W, and we can calculate length of V, length of W, and the cosine, and we'll leave cosine of the angle between them unknown because we don't know what theta is. So we're trying to find the angle theta between these. Well, V dot W is just this times this plus this times this, right? It's 1 times minus 1 plus 3 times 2. That's what the dot product is defined to be. This times this plus this times this. This number, 6 plus minus 1 is 5. Now, what's the length of V? The length of V is the root sum square of its components. Square root of 1 squared plus 3 squared, right? What's the length of W? Square root sum square of its components. Square root of minus 1 squared plus 2 squared. What we found by our theorem is that phi equals square root of 10 square root of 5 cosine theta. So what must the cosine of theta be? It must be the cosine theta is 5 over square root 10 square root 5. Wait a minute, the bottom is now square root 2 square root 5 square root 5. If I just break up square root 10. And now square root 5 square root 5 is 5, cancels the 5 on top. And this is 1 over square root 2. Cosine theta equals 1 over square root 2. I wonder what angle that could be. I know what it is, right? Because 1 over square root 2, if I multiply top and bottom by square root 2 to rationalize it, is equal to square root 2 over 2. Right? By rationalizing, multiply top and bottom by square root 2. I recognize that comes from a 45-degree angle. This tells me that theta is 45 degrees. So let's use radians as often as we can. Wait a minute. Maybe I've got the wrong quadrant. Did I have the wrong quadrant? No, this is not like the tangent y over x problem where you have to figure the quadrant. In this theorem, there is only one angle possible whose cosine is between 0 and 180 degrees and satisfies this relationship. And it's the arc cosine. This is the final answer, and I'll write it out now why. You don't have to worry about is it in the right quadrant. Is there another angle that has the same cosine? Angle between them. Oops. So we have this note based on the theorem that P dot W by the theorem is always equal to length of V, length of W, cosine the angle between vectors for any non-zero vectors being W. Well, if they're non-zero vectors, then they can't have zero length. The zero vector is the only vector with zero length. So we can divide through and find that V dot W over length of V, length of W is equal to the cosine of theta. All right. This glare is getting powerful. I'm not sure if I can get this close to reduce it or not. Hope you can see all right. I'm worried you can't. I guess that's hopefully that's good now. About the best I can get it, I'm afraid. All right, so a lot of books will write this formula that tells you the cosine between the angle between two vectors. But now, because the arc cosine is the unique angle that has this cosine and is between 180 degrees, angle theta between 0 degrees and 180 degrees with the given cosine, only one of these, we can then write as the next step, because of this theorem and this fact, therefore, three dots mean therefore in mathematics, theta is actually always the arc cosine of this number. So this is a useful formula that can be derived from that big theorem that in the angle between any two vectors is always the arc cosine for non-zero vectors of V dot W over length of V, length of W. That's the angle between. Call that a corollary to the theorem. You know what a corollary is? Corollary is just a theorem. If it follows quickly from another theorem, and it's a useful result to call it a theorem, then instead of saying theorem, you might want to say it's a corollary. It just means it's the theorem that followed quickly from the other one. Right? That's all it is. You get to choose to call it a corollary if you want. There it is. Let's try another one. Not always do these vectors come out with a nice angle between them like we got in the last example. Right? Find angle between the vectors b equals 4, 3, and w equals minus 5, 12. I wonder what the angle is between those two vectors. We could draw them just for fun, right? 1, 2, 3, 4. 1, 2, 3. So there's this vector b. We'll put it at the origin for convenience. W is minus 5, 12. 1, 2, 3, 4, 5, minus 5, 4, 5, 6, 7, 8, 9. Well, it's way up here. There's minus 5, 12, the vector to that point. So the angle between them is going to be this one, not this one. What angle is that? All you have to do is go straight to the formula. Theta is the arc cosine of v dot w 4, 3 dot minus 5, 12 divided by the length of 4, 3 times the length of minus 5, 12. And we just need that computation. It's the arc cosine of 4 times 5, 4 times minus 5, right? This is the dot product. This times this plus this times this. Right? These two multiply plus these two. Plus 3 times 12 divided by, well, what's the length? That's root some squared. Square root of 4 squared plus 3 squared here. Square root of minus 5 squared plus 12 squared here. Right? This is the arc cosine of minus 20 plus 12, 30 plus 36, excuse me, is 16. Right? And in the bottom, square root of 3 squared plus 4 squared is 5. Square root of 5 squared plus 12 squared is actually 13. And this up comes out to be 169. And so we have, it's the arc cosine of 16 65ths. You can run that on your calculator and get a decimal approximation. So this is what you do when it's not a special angle. You just run the arc cosine function. It always works for non-zero vectors. If the zero vector, there isn't angle specified. It's not apparent yet how useful this dot product is, though. It's very, very useful. Next concept you can define with them, and it tells you right away the angle between vectors. That's an important concept too, but moreover, it does lots of neat things with projections. So projection of one vector onto another. We will make this definition, and then I'll show you why we make it. The projection of V onto W is, given this notation, projection V onto W, V dot W over the length of W squared times W. That'll be a definition. There's a lot of things to memorize today. That's the thing. It's a hurry-flurry section, but none of it is too terribly difficult. It's just a, but you know, if you ever took a foreign language, you have a lot of words to memorize. It's still hard, right? Because there's a lot. All right, even though it's just rote memorization. So same thing here. This isn't too hard to memorize, but it's a lot to memorize. The projection has that definition in Well, I like to draw this picture. If I have a vector v and I have a vector w, what would I like to think is the word projection means? What I'm thinking of is way off in infinity here, there's a sun shining down, and it makes a shadow, and the vector here is projected down onto a vector here on top of w, moving in the same direction as w. And this one we want to think of as the projection E onto w. If that's the case, this is the definition, right? To get this vector, that's what we have to do. And here's why. We need it to have the right length, right? What is the length of this thing? What should be the length of if this is going to be the projection, what should be its length? Well, remember how triangles work? If this is V and W, then this is theta, the angle between them. And a right triangle, this side is length of V times the cosine of the angle, right? This side is length of V, cosine of the angle. So that this over this is the cosine of the angle, right? This over this length is the cosine of the angle. That's true in any triangle, right? If you have a hypotenuse C, then this is C times the cosine of the angle, and this is C times the sine of the angle, so that they have the right ratio. Right? So this one will be length of V cosine theta. And now, what is the vector I want? What is this vector here then? This is its length. What's its direction? It's in the direction of W. And we can make this following definition. A unit vector, it's just what it sounds like. It's a vector of length 1. Unit length, right? Right, in other words, length of unit vector is 1. All right. Now, here's what's nice about this. If I take W divided by its length, what do we know? Well, we don't know how to do division yet. What does this mean? This will mean the number 1 over length of W times W. In other words, whenever I divide a vector by a number, right, the length is a number. That means multiply by 1 over the number. That's how we'll define division by a number. Right? Well, what is the length of this? The length of this is the length of, well, you're multiplying this by a number, so it's W1 over its length, W2 over its length. Now we're taking the length of this vector, because we're multiplying each component by 1 over the length of W. And now, what's that? Well, you root sum square them, right? It's W1 over root W1 squared plus W2 squared is W1 divided by the length. That's the first component of this one. Let's do one more here. Say this is the length of the vector with these components, W2 over length of W1 squared plus W2. So it's the length of this vector. But now that's the root sum square of those things, right? Square root of this one squared plus this one squared And that is equal to the square root of W1 squared plus W2 squared on the top, and combining the numerators, over each denominator of W1 squared plus W2 squared. Oh, it's the square root of 1, it's 1. If you divide a vector by its length, right, getting 1 over the length times the vector, you get a unit vector, right, because the length of the result, I'm sorry, so this one has length. One, right? We show that if we take the length of this vector, it's this, we get 1. So it's a unit vector. Now, what we can do is this. Vector W, or the projection, what we want is to have this length and this unit vector direction. How the projection of V onto W will be the vector of this length, or this length, but this length is equal to, let's see, if I rewrite this, I could write this as length of U, length of V, multiplied together, times the cosine of the angle between them, divided by the length of V, length of W. Divided by the length of W, right? So I just multiply this top and bottom by length of W, it doesn't change it. And so it's actually V dot W over the length of W. So that's the length of the vector we want. And here's a unit vector in the direction. So W over its length, the unit vector in the right direction, sometimes called a direction vector. It's the unit vector in the same direction as the vector. So we can get the projection simply by taking the length, which we found is V dot W over length of V, length of W, times a unit vector in that direction, which was W over its length. That will give us the vector we want. We'll take a unit vector and make it this times as long. It'll be the right length in the right direction. This gives us the direction. This gives us, this scales it so it's the right length. And now what does that multiply out to be? That's just V dot W on top over best put this here. The length is just V dot W over length of W. I put it next to V dot W over length of W. So this is V dot W over length of W squared times W. Just rewritten it. Group all these things together and put them down over here. And then just W is left here. So rearranging this, that's how we define the direction. We define it to be that because it makes it this vector right here. That's the shadow of this vector onto W. It points in the direction of W as the length of the shadow. So we'll call it the projection. This is extremely important in physics. I guess we'll have to do something with that next time. But also this concept here is important too. If you take any, let me not carry it too far. I'll give you the homework, and we haven't quite finished this section on the dot product. We've got a ways to go on it. But at least try these elementary problems on vectors. And we need to do vectors in 3 dimensions too here, but in 11.2, this looks like a lot of problems, but they're very easy. 1, 3, 5, 9, 11, 13, 15, 21, 23, 27, 47, 55. Then out of 11.3, let's look at 1 to 9 odd, 15, 23, 25, and 27. So we haven't finished these, but you can start looking at these for next time. And we'll finish this next time, and then you can do all the rest of these. 3 questions, and this is quite a lot of material, as you can see, and we haven't had an example on projection. We'll just say, here's the derivation. Next time we'll do something. Thank you for coming in tonight. I'll see you again next time. Send me questions by email too, as you have them.